Okay, hello everyone. I'm Jayne Birkby. I'm at the University of Oxford, but I had the enormous pleasure to do my PhD here at the IOA somewhat after it started, it's 50 years. And actually the field that I'm working in only started really with observational evidence in 1995, the actual detection of exoplanets around sun-like stars. The first exoplanet atmospheres, which is what I'm going to be talking about today, the first observational evidence of that was only in 2002. That was in transmission, and then actual thermal light coming from an exoplanet was discovered in 2008. The work I'm going to show you started in 2010. So we've got about 14 years of exoplanets at high resolution, in high resolution spectroscopy. So thank you to Anders for sort of motivating the theory behind planet formation and its intimate link with exoplanet atmospheres. I want to show you sort of the breakdown of the types of planets that we find out there at the moment with the sensitivity that we have approximately out to about 100 days with the Kepler Space Telescope. And then there's sort of a gap, and then we're sensitive out then to widely separated planets as well, at sort of tens to hundreds of AU. So with the giant planets, what I'm going to show you is we're sensitive to things like their composition, their atmospheric structure, and their winds and their climate patterns. Okay, these planets are big. We can do quite a bit of signal to noise on them. As we go down in mass and size, we come into the Neptunes and the sub-Neptunes. We don't really know what sub-Neptunes are. There's a degeneracy in their mass and radius with what their interior and atmosphere is. I'll show you a bit more in a minute on that. But with them, we're interested in their atmospheric evolution. They're susceptible to mass loss if they're too close to their stars. They seem to be hazy. We see lots of flat spectra, and we want to understand their interior structure. And then we have the small planets, perhaps the things that we're really, really interested to see. How common are Earth-like planets? What can we say about them? Do they have atmospheres? Most of the ones we know are around M dwarfs. M dwarfs are very active stars and can strip an atmosphere. So we don't know yet if these rocky planets around M dwarfs have atmospheres, but they're our best targets. We might be able to say something about their surfaces, whether they have oceans, and ultimately whether they're habitable. Okay, but exoplanets are complex. They are some of the most complex objects that we study in astrophysics. They require both spatial and temporal treatment for their chemistry and dynamics. Even for what I think is the most simplest case of an ultra-hot Jupiter, you heat everything up. There's not too much complex molecular chemistry going on. You're dissociating your molecules on the day side. You're recombining on the night side. You might have clouds on your westward limb, offset hot spots on your eastward limb. And your whole atmosphere is experiencing a wide range of processes, from atmospheric escape, photochemistry. We're interested in the structure of the atmosphere. Does its temperature have an inversion in the same way the Earth does? Our inversion is caused by ozone absorbing UV light and heating up our upper atmosphere. This can happen with other molecules like titanium oxide in ultra-hot Jupiters. Then below that, we might have clouds and hazes, vertical mixing, circulation, all kinds of things going on. And all that information is stuffed down into a single pixel. And we have to extract that information. So the more avenues that we can take to get at the information that's there, the better. So wavelength, resolution, spatial dimensions if things are widely separated. So my talk is about high resolution spectroscopy, but it would be remiss of me not to show some of the best low resolution data that we have, which is just starting to appear from JWST. I wish we had this 10 years ago. But you can see now, so this is showing you a hot Saturn. This is some of the early release data. You can see beautiful light curves. These aren't models or simulations, it's real data. And you can see really obvious features now. So we have, for example, carbon dioxide over on your right. And even in this case, the interesting thing that came up was at 4 microns, the detection of SO2, so direct evidence of photochemistry in the atmosphere. If we push down in mass towards those sub-Neptunes, we can see that we start to detect molecules as well, methane, water, CO2. But we have this degeneracy for these objects that we're still trying to understand. In this particular case, for this sub-Neptune, there was no ammonia. There should have been, so where did it go? Has it been absorbed into a liquid water ocean? Or is there a combination of this vertical mixing, photochemistry, the metallicity of the atmosphere, with a magma ocean that can create, instead of having a liquid ocean, that maybe you have some miscible water H2 atmosphere that you're looking at. And so we still need much more data on these to understand what's going on. So the data that I'm showing you here, I've called it low resolution. Contained within one of these data points, if I was to have this data point at, say, 760 nanometers, so over in the optical, where the oxygen band is, in just one of those data points at high resolution, I would see this. Many, many individual lines. There's lots of information at high resolution. And if we can access this, we get all that information, and because the spectral pattern is so unique, it's very hard for random noise to mimic this signature. So we have robust detections of molecules as well. We can separate out the molecular bands. So the way high-resolution spectroscopy works for close-in planets is we use the Doppler shift of the planet, and we observe it as it goes through its orbit. And what you find in this cartoon at the bottom, I'm showing you the curvy lines are a high-strength injection of a planet atmosphere. So it's not realistic, but if you could do that, this is what you would see. You'd see each line in the planet spectrum traces out the radial velocity curve of the planet itself, not the star, the planet itself. So we tend to observe between either transit or just before and just after secondary eclipse. We do not need the planets to transit to do this. We are directly detecting light from the planet on its day side. And the way that we extract the planet signal is we do a cross-correlation. So we remove everything that doesn't change in wavelength over time, and we're left with noise, but buried in the noise is the planet signal, and all the individual lines have a signal to noise of less than 1. So we run a cross-correlation with a model, and when it matches up, we get a signal. And I can do that for a series of spectra, and you get something like this, and hopefully you can see a dark trail sort of moving diagonally across. And this was the first detection in 2010 of CO, carbon monoxide, in a hot Jupiter atmosphere. This was quickly followed in 2012 by a detection of CO on the day side of Tau Bu, which is a non-transiting planet. Now here I've rearranged this trail in velocity space. So you're seeing the orbital velocity on the y-axis and the systemic, so sort of the star co-moving velocity on the x-axis. And actually, so from this, you see that you directly get the inclination, and so you can measure the masses directly as well. This was also then followed the year later in 2013 with the detection of water using the high-resolution method. CO is a more simple molecule than water. Water has many spectral lines, and it might have been confusing for the cross-correlation to detect this, but fortunately not. So it meant that we could do both simple and more complex molecules, which was a good indicator that in the future, with a big enough telescope, you could use this to look at biomarkers. So in the intervening 10 years, there was lots of hard work making spectrographs do this work. Particularly, we lost CRIRES at the VLT for about 6 years in between there, but it's come back now. We have CRIRES Plus, there's Espresso at the VLT, and a huge suite of high-resolution instruments. And so these detections are now basically routine. They're not easy, but they're routine. So here I'm just showing you, for example, a spectral atlas from one hot Jupiter. I'm showing you lots of different metals in the atmosphere. For this particular hot Jupiter, if we keep studying it with more high-resolution data and actually have enough resolution to break down as we go through the transit, we can actually look at what different limbs of the atmosphere are doing. And you can see that for ingress and egress, both for the morning and the evening limb, that we can measure the abundance of iron as we pass through those parts of the atmosphere. And it's different. Okay, there's a spatial distribution of iron in the atmosphere that isn't uniform. So we're really starting to get at those 3D effects. We can also compare how those metals stand in comparison to the host star abundances and our protosolar abundances, and start to see whether or not we see any significant differences. And does that tell us things about formation or processes in the planet atmosphere? So you can see our alkali metals on the left, strongly ionized, so we see those drop down, but more or less things in between seem to match reasonably well. And then as we go to these ultra-refractory species, we actually find that they're being trapped on the night side and they're raining out. So they're gas on the day side, they go round onto the night side and they rain out. And so we can actually see the processes happening in these atmospheres. So not only do these planets tell us something about formation, they're actually laboratories for us to push our understanding of physics and chemistry to the extreme, to really understand what we're doing. At the moment, if we do retrievals on atmospheres of hot Jupiter-like planets with high-resolution data and measure things like carbon-to-oxygen ratios, at the moment we're basically doing as well as JWST. So in red is the prediction from modeling ground-based high-resolution data of a hot Jupiter, and then blue is what JWST saw of the same planet, and you can see that the model and the data overlap very well. Now, as we go to smaller planets where our signal-to-noise gets harder, the combination of both high-res ground-based data and lower-resolution space-based data is going to be really important for pinning down these abundances and understanding their formation. And we want to tie this to example, if we look at trends between the mass and the planet to proto-solar element enrichment, we see that our solar system seems to lie on a trend, and different formation models would predict different locations in this diagram for the planet. And we can see that this one is lying below close to solar composition. So most of what I've shown you has been these metal species or molecules where we have many lines, and we can do that cross-correlation. We don't actually need to do the cross-correlation if we have a strong enough line. And a good example of this is the helium triplet. This is actually, it's 3 lines, but basically you can only see the one, but this is a resolution of about 100,000. And what you're seeing there is the hydrogen in the atmosphere, and what it probes is whether or not that atmosphere is escaping. So this is work back from 2018, looking at a warm Neptune. But more studies have been done. This is one for a hot Jupiter to actually try and model what that that escaping atmosphere looks like. And these are some hydrodynamic models from Caroline Morley's group, showing you for the planet. You can see it shows the transit phase. We have pre-transit, transit, post-transit. And this is the model that they're able to back out from this high-resolution data. So the leading trail is showing you escaping atmospheres on the day side, and the trailing trail is showing you escape from the night side. So we can really start to model in 3D what's going on in the environment of these planets. Okay, so we've looked at composition and we've looked at potential escape. If we can have widely separated planets, those planets are freely rotating. And if we are able to extract the cross-correlation function for those planets, we can actually see that they're broadened. So in the dotted line here is what we expected to find from the instrument resolution, but what we found was the solid line that shows you the broadening of the atmosphere. This was about an 8-hour day, and it gives us an insight into the angular momentum that planets acquire as they form. Similarly, for a close-in planet, we can also look at the dynamics. This is again looking during the transit, and hopefully you can see up here, there's not one trail, but actually 2 trails. And this is evidence of a supersonic jet rotating in the hot Jupiter. But the fact that there's a bit missing in the middle, if you do the full modeling, it implies that there must be clouds on the poles that are suppressing the signal that you would expect to see in the middle of those 2 lines. So you get your 2 lobes and then nothing in the middle. So we're really starting to probe the dynamics of what's going on in these atmospheres. Okay, I want to spend the rest of the time forward thinking and looking to the ELTs. So the ELT is going to be an exoplanet atmosphere characterizing machine. It has a suite of instruments, and 3 of those in particular are going to be amazing for exoplanet atmospheres. So at first light, they will be Metis and Harmony, and then very soon afterwards, Andes. So Andes will have both an IFU, so an integrated field spectrograph, 100,000 resolution, as well as a seeing limited fiber that can do transmission spectroscopy. And then both Harmony and Metis are IFUs. So all that means is that if you take an image, effectively, for every pixel in the image, you get a spectrum. Okay, so first of all, the ELT will basically do for exoplanets what the VLT does for stellar spectroscopy. Okay, that's where we're going. So we're kind of almost there. With the VLT, we can look at a few individual lines, very strong lines in exoplanet atmospheres, and actually see the individual line and fit them. And this is a recent paper showing iron lines, individual iron lines that we can fit. But with Andes, we get all of the individual lines that form at all different places in the atmosphere. So I don't know if there are any M-dwarf fans in the audience, but this kind of spectra that we'll get, you actually see band heads from molecules. This is titanium oxide or even CO lines. And so you have lots of detail to probe what's going on in your atmosphere. And so I think this is the game-changing nature of the ELT, okay, that we're going to do stellar-like spectroscopy for exoplanets. And I think there's many things that we haven't even thought of that we will find out by doing this. Okay. We can even, when we have high resolution, we can look for line profile changes as things rotate into view. So imagine if you had a storm on your surface of your planet, like the Great Red Spot on Jupiter. If that rotated into view, the overall flux of the disk of the planet would change slightly. And as it passes in front of the blue shifting or the red shifting limb, you would get a change in your line profile. And you can actually back out a map of your planet. This has been done for brown dwarfs. Okay, this has been done with the VLT. So we think that we can do this with the ELT. And just to show a bit more JWST data, this particular brown dwarf, this is what's going on with the light curves as a function of wavelength. There's all kinds of variability going on. And it tells you that as your different wavelengths probe different parts of your atmosphere, you're seeing different structure rotate in and out of view. Now from the spectroscopy, we get a V sin I, and from the light curves, we get a true rotation period, which means in principle, if we can do this for exoplanets, we can actually solve for the inclination angle of the planet to the star, which would tell you the seasonality of that system. I think this will be quite hard for Earth-like planets, but it might be quite interesting to see it for slightly larger planets and how it impacts the climate that they're able to see. Okay, so I've mentioned METIS on here. METIS actually works in the 3 to 5 micron range, which contains lots of biosignatures, particularly at high resolution. There's a huge amount of information here. But to date, it hasn't actually been shown that we can use this method here. And there's 2 reasons for that. One is that the telluric contamination, as you go beyond about 3.5 microns, becomes very strong. And secondly, and most importantly, the sky background jumps up. We want to be photon dominated, but the sky background can reduce our sensitivity. So with my student, Luke Parker, we decided to test this with VLT, with CryoRes Plus, which reaches down to 3 to 5 microns. And I'm just showing you here in the center, this is at the point spread function of the star, and you can see beta pic there at its contrast ratio. And so you can see that background level rising as you go into the infrared. And so the contrast that we're trying to dig down to is at least a factor of 100 here. But we persevered. We put our slit down on our star and planet, projected it onto our detector, did lots of complicated analysis to remove the star. I'm not going to tell you what that was. And then we did a cross-correlation at the planet position and everywhere else. And the question is, did it work? Can we use the M-band to do this? And of course, we can, otherwise I wouldn't be showing you. So we detect CO and water, so we know that it works. And it's even better news for METIS because we get a D to the 4 reduction in the background noise. So all looking good. We know this is now going to work. We also saw some evidence of SIO. We still need to follow it up. It's tentative, but it's a bit strange because we think there should be MgSIO3 clouds on this planet, but the fact that if we see SIO, it means somehow we're either seeing below the cloud deck or it's patchy and we're seeing bits coming through it. Maybe it's not there, or maybe the clouds are transparent at the wavelengths we're looking at. So lots more data needed, but if we can trace SIO, it gives us access to these refractory materials that help us then connect that atmosphere back to how and where it formed in the protoplanetary disk. Those refractories tend to stay in one form, whereas volatiles can pass between different phases. SIO is also expected to be in the outgassed silica atmospheres of lava worlds. So we're going to try and do this in the M-band. Okay, in the last minute, I want to talk about reflected light. So if we look at the reflection spectrum of Earth, we have many biosignatures. Reflected light tells us about temperature and energy balance, tells us about the cloud properties, their scattering, might tell us about surface structure, oceans glinting in reflected light, and again, atmospheric composition and biosignatures. So this is what we want to access. Proxima b is our best target for doing this for a nearby rocky world. But when we do this, the reflected light is the stellar spectrum plus the planet spectrum. So what you see is a combination of both. You need to model your planet well and your star well. So far, this technique hasn't worked to detect anything, mostly because we've only looked at dark planets, but we're reaching contrasts of the order 10 to the minus 6, which is enough to start detecting Neptune-like planets. So we're doing this right now with 4 UT modes, so 16.4 meter effective mirror diameter at the VLT. I'm not going to show you the results because I want to be certain when we show it, but maybe there's something there. Okay, so if we could do it and we do a simulation for harmony, this is work that Sophia Vaughan has been doing. We inject a planet, it's a cube, so we do our cross correlation for the whole cube, reconstruct it, and at 75 milliarcseconds you can detect an Earth-like planet or Proxima b-like planet using harmony, but Proxima b is hidden behind the mask of harmony, so we're working with the harmony team to try and change the mask before we go on sky. So if we had no focal plane mask, you need it to stop saturation. We can't not use it, we've been told no. But broadly, the different masks that we've tried, you need an integration time of about 30 hours. If we offset the mask, we need to know the orbit. We don't know that yet, so we're working with the harmony team to try and change this. However, reflected light is the driver for the Habitable Worlds Observatory, and Andes has identified a golden sample that it can target on similar or less timescales to actually deliver a sample of reflected light. And for different scenarios for Proxima b, it can take between sort of 1 hour and 50 hours to actually make a detection of various different biosignatures. The story is similar for Metis. About 10 hours, we think we can start to access the atmosphere of Proxima b. So I got to go to the ELT in October. It's happening. It's coming soon. I leave you these take-home messages, and 2 things I want to highlight is that in early 2030, we will do a full characterization of an Earth-like, a rocky planet. We'll see if it's Earth-like, to see if it has an atmosphere. And that combined power of Metis and Andes together at 100,000 resolution is going to be revolutionary for exoplanet atmospheres. Thank you.